So for recording purposes, this is tough questions for the CXC exam, right? I know I'm saying the word CXC, but it's for regular boring Form 3, Form 4, and Form 5 work as well, okay? All right, so here is the first question, right? Now, I tried to make it a little bit funny and whatnot, well, my version of funny, right? So here's the question. They said Z is a gas that has a physical and chemical property to ammonia. So you have some gas. We don't know the actual name of the gas. We're just calling it Z. And all we know is it's not ammonia, but it's very, very similar to ammonia. How should we collect a pure, dry sample of Z? So we have to use our imagination in this question. That we're performing some experiment. We have no idea what the experiment is. All we know is that in the experiment, the gas Z, the mysterious gas Z, will be produced. And we want to know how we're going to collect a pure sample of Z. Like we want Z alone. We don't want anything mixed up in it. Pure Z. And the only hint we have here is that it's very similar to ammonia. So the number one question is going to be this. But sir, how do they create ammonia in the first place? Like if I were to open a chemistry lab now and I throw oil into the lab and say, make ammonia gas now. The first thing you're going to ask me is, I don't know, or tell me is, I don't know how to create ammonia gas. I know my teacher did ammonia in class. He mentioned ammonia and whatnot. But I don't think he ever teach me how to create ammonia. Also, they said Z has similar properties to ammonia. So the next question is going to come in your head. What are the properties of ammonia? I know I did ammonia, but nobody ever tell me the properties of ammonia or did it enough. So I know the properties of ammonia. So on the screen here is one of the most popular ways to create ammonia. So I'm going to put a little arrow here, right? Believe me, I'm not going to ask you to draw the diagram. That's just for me to explain. This is one way to create ammonia. How much of you all have done this experiment? You take ammonia chloride, well, a solution, AQ means solution of ammonia chloride. Now, ammonia chloride obviously is not the same thing as pure ammonia. Ammonia chloride is ammonia mixed with chlorine, right? And what they usually do is mix it with some solid calcium hydroxide. These two things are very easy to find in almost any chemistry lab. And it just so happens, when you mix the two together, you get pure ammonia, calcium chloride, and some water. Now, here's the thing, right? Ammonia is a gas, right? So when you mix everything in the flask, when you mix these two things in the flask, well, what's going to happen? The ammonia is going to, well, the calcium chloride will stay, everything will flow down over here, right? But the gas will what? Rise. The ammonia gas will rise. The calcium chloride will stay back. But the problem is, remember, this is a very hot experiment. When the ammonia gas is created, don't you think some water vapor will be mixed in with the ammonia? So what they usually do, when the ammonia is rising, it takes a little bit of water with it. But remember, the question said we wanted pure ammonia. We don't want ammonia mixed with a little bit of water in it. So I don't know if your teacher mentioned this, right? Or you may have seen it in a textbook. How do you get rid of a little bit of water when it's mixed with something else? You have two choices. In this experiment, they use calcium oxide. So when the ammonia tries to flow through the calcium oxide will remove the water part. And what will happen? Pure ammonia will end up in the little test tube here, and that's how you collect it. Now, in chemistry, as far as I can tell, there are two ways to remove water. One way is calcium hydroxide, or did you all notice sulfuric acid as well can also be used to dry out things, mainly gases. I'm sure you all have seen that somewhere in some experiment at some point in your CXC career. So if we are making a gas Z that is very similar to ammonia, maybe our experiment should resemble this setup, right? So the correct answer is obviously B, right? Calcium oxide and collected by the upward delivery. But here's what I want. Oh, by the way, in case you didn't know, ammonia is highly soluble in water. You could dissolve it in water. And ammonia is less dense than air. So that's definitely going to float up to the top very, very easily. So here's what I need for you all to take down. I need you all to take down the thing in yellow, the correct answer only. Take down this and 1, 2, 3. Okay? Do not draw the diagram. Okay? This is an actual CXC multiple choice question. But you see how by just discussing this question, you not only learn the answer for the multiple choice, we get an excuse to investigate the other parts of the syllabus and other potential questions. Let me know when you are finished. Typo. It's this word supposed to be an, right? So both of them are very good drying agent, right? Meaning that they're good at removing H2O from substances. So let's look at the second question that, most people don't know the answer to. I believe I discussed this one last year. So this question here deals with aluminum, like why aluminum doesn't rust. Well, the correct word is actually corrode. Why does aluminum last so long? So quick question. If I have a block of aluminum and a block of iron, Fe is iron, and I put two of them outside your house, right? So we leave them in a savanna. If I come back after 2 years, which one will be in better shape? Which one will be in better shape? And well, from last term, aluminum will be, not iron, aluminum will be the one in better shape. That is why, well, when you're making window frames, aluminum costs more than iron window frames. Iron window frames in a few years, that gone through. If you don't take care of that, it's gone through. Aluminum can last for like 10 to 20 years if it's done properly. You see, the thing about it, well, we all know in the atmosphere, right, there's oxygen, right, O2. What usually happens, the iron will react with the oxygen to get Fe2O3, better known as rust. So the rust will start to, I use little red dots here, right? The rust will start to form on the surface of the iron. But everybody knows rust is flaky. If you take your fingers, you can remove some of the rust, okay? So the thing about it, the Fe2O3 forms a layer around the iron, but it doesn't form a proper layer. If it's flaky and more oxygen could get in between and keep attacking the iron, and of course, if the oxygen keeps attacking the iron, then eventually all exposed parts of the iron will eventually turn to rust, right? So it's almost the same thing with aluminum. When oxygen reacts with aluminum, it forms Al2O3. Just like how iron will form Fe2O3. But the nice thing about Al2O3, it's not flaky. It forms a nice solid layer. So that means once this solid layer is formed, no more oxygen can reach what? The aluminum. So the oxygen tries to destroy the aluminum, but in the process creates a protective layer, thereby preventing any more oxygen from coming in contact with the aluminum. Hence, aluminum will last longer. Okay? And that is what this note is trying to say. All right? So I think I did I think this one, how we did it already, it shouldn't be too hard to explain, but take down the question, take down the correct answer, and guys, yes, I want you to take down this note over here. I know I'm asking a lot, right? But you go thank me when this comes in the exam, and you don't have to think too much about the correct answer, right? Right. Right. Let's see the next question that usually gives a lot of problems. Now, don't worry, I'm not going to make you draw that table. All right. But to me, this question, if I saw, I can just imagine if a student like you all saw this in the exam. To me, I would have never expect you all to figure this out. So what happens when aqueous silver nitrate is added to aqueous potassium chloride? Now, there are two obstacles to this question. First of all, you have to assume that the student has the ability to do what? Balance this equation, right? How much of you all could say with confidence that you all could have balanced this equation, right? It's just a matter of the, if you look at it, the potassium takes the silver place, and the silver takes what? The chlorine, the potassium place. In other words, the silver and potassium switch places, okay? Right. So, fine. So that is the first obstacle, which I can see most people not getting out. To be honest, I know most of you are good at chemistry, right? But it's just certain things over the years, I realized that students, they just throw their hands up in the air when they see certain things, okay? Now, here's the thing. You have to realize, according to this table, which you are supposed to memorize, right? I know how you're going to plan to memorize this for the exam, right? But silver chlorides, look at here. Silver chloride is what? Insoluble. So that means when the reaction takes place, it will form what? A solid. Usually when something forms a solid, it will form what? A precipitate. And on top of that, you have to know it's a white precipitate. So you see how much things the examiner assumes that you know for this quote unquote wonderful question. So in my opinion, right, it's best just to memorize the answer for this one, okay? And the nice thing about multiple choice questions, it is repeat over and over and over and over, okay? So you're going to take down the question, you're going to take down the answer, and you're going to take down this, and I want you to add this hour. I want to add in this note here. I want you to make a note here. This is a white, not just a precipitate, but a white precipitate. right? This one, I'll give you a couple minutes and we will move on, right? Let's go. All right, so let's move on to number 4 and see what we have. Right, I'm not gonna make you draw the table, right? How much people have seen this table here in school, right? I believe most teachers stop giving students this table to learn off because they have so much to learn off already, right? But I would explain what the table is about, right? You all heard me mention something called thermal decomposition. Thermal decomposition is when you add heat to something. So you give something heat, a compound heat, and then it breaks down the compound into different compounds. Okay? That is all thermal decomposition is. Once again, it's when you add heat to something and the heat changes it into different things. Simple concept. So different things decompose differently. Different things, if you heat them, will naturally break down into different substances. So this table is supposed to give you an idea of how different substances break down. But I know from experience, the average person not going to memorize this table. You all have so much, you all doing how much subjects? 8 or 9 subjects? You all not going to memorize this. So this is a question I want you all to remember. When copper 2 carbonate, right? Let's look for the carbonates here. So we're in the carbonate section, right? And it's copper, right? So that means it's this section of the table we are looking at, right? When copper carbonate is heated by itself in a test tube, a gas is evolved and a black residue is created, right? This gas is expected to do what? Notice the gas that is produced. So we got a different color here. The gas that is produced is what? Carbon dioxide, right? And we all know what carbon dioxide will do. When you mix it with lime water, better known as calcium hydroxide, you get a white precipitate. Okay? So guys, I want you to take down the question and I want you to take down the answer to memorize for the exam, right? Right, so as far as I can tell, right now, I know some people are saying, but suppose they bring a question on something else, like instead of the carbonate, what about the nitrate or the hydroxide? Well, but what I did, I went through the multiple choice questions and I started to pull out the ones that actually do come. Remember, multiple choice questions at this point in time doesn't change. It just keeps repeating itself over and over, right? So it's a little strategy to help you with the exam. Let's see the 5th one. All right, so I never seen this one. And to be honest, well, all the years I've been teaching chemistry, right? Sometimes people is given the old books and thing from school, the notebooks and thing. I have never really seen a note on this, but I keep seeing this question repeating in the multiple choice, right? And a little bit in the structured paper. So which of these statements are about sulfur are true? So here are 2 true things and 1 false things, because the question is they could ask you to list 2 true things or ask you which one is false, right? Sulfur is used in the vulcanization of rubber. So I know you are going to ask, what is vulcanization, right? I will explain that just now. 2, sulfur is used to extract in the extraction of iron from iron ore. This is definitely not true. If you look back in your notes, when we were doing the extraction of iron with the big chimney, you will see that sulfur is nowhere in that process. And sulfur is used in the manufacture of explosives. That is true. right? Now, most of this stuff is probably brand new to everyone in this class, even if you did this topic in school, right? Or completed the syllabus, you're probably saying, well, you never hear about the properties of sulfur before, and you definitely haven't heard about vulcanization. So vulcanization is basically, it's a synthetic, you all know rubber is a, well, rubber could be natural or it could be synthetic, right? So let's say, right, if if you have rubber, right? So this string is supposed to represent rubber. Which one do you think will be stronger? The first one or the second one? In the second one, you take the strings and kind of connect them individually, well, to each other. The second one will obviously be what? Stronger, because the layers are kind of joined to each other now. This joining of the different layers of rubber to make it stronger, and obviously it changes the property a little bit, is called vulcanization. And the correct word for these links is called cross links. Okay, so now you know a little bit about what vulcanization is. And if in a structured paper they ask you to describe what is vulcanization and why do people do this process, well, you have something to write for the examiner now, right? You take, everything on the screen, every single thing, and yes, I want you to draw the diagram as well. Because in the CXE exam, if they give you this diagram and ask you to complete the diagram to show vulcanization, you will need to add in what? The cross links to complete the diagram. Let's see the question number 6. Right. So this one here, now we haven't done organic chemistry as yet. We're going to be starting that next week, right? But this here was a question, even if we did the whole of organic chemistry, right? You're going to realize when this question came for CXC, people will just shrug their shoulders like, what? Okay. So glucose, I think you all know that for those who are doing biology, it is possible to convert glucose into what? Starch or cellulose, right? How much of you all do biology here and you're familiar with that, with the concept that glucose can be stored as starch or something called cellulose, right? So in the exam, they ask you, well, what is the name of this process by which we convert glucose to starch? And in chemistry, the correct answer is condensation polymerization. But when we do organic chemistry, you're going to realize that there are two types of polymerization. One called condensation, which is on the screen, and the other one is called addition polymerization. But that will be one of the last things we ever do in chemistry, right? So everything is on top here, right? There's something called natural condensation, which happens in nature, and there's synthetic, man-made types of condensation, right? And over here we have a kind of definition of what condensation polymerization is, right? So I need you to take down everything on the screen here, but I guarantee you, people who do the whole of organic chemistry, if they see this question in the exam, they're gonna be like, I have no idea what the correct answer is. But now you know. Condensation, polymerization. Right? Glad you all are having fun with the answers. Right. Number 7. So this one I'll definitely want to discuss, right? Because this definitely can help you in the paper too as well. A solution X, so this mysterious solution X is added to acidified aqueous potassium iodide, which turns brown. Afterwards, starch is added to the solution, which results in a dark blue coloration. what does X contain, right? Now, I'm going to start with the most obvious tests, right? Everyone here knows at least about the starch test. Like, how do you test for starch? You usually drop what? Iodine on it, a solution of iodine. And according to this, if something contains starch, the iodine will turn what color? Purple. A lot of people are familiar with this. I think that's part of biology as well, right? Seems familiar? The star test, right? That's real basic. I think that's something in Form 2 or Form 3 you just learned. So the food test, yes, someone has it correct. The food test. Now, I want to dig into this a little bit more, right? Now, they said when you took X and you mixed it with potassium iodide, okay? In case you all don't know, potassium iodide is clear. It has no color. It's colorless, okay? I'm going to call it clear. Should I put colorless? But what happens, right, is that X will whatever is happening, X is displacing the iodine. So remember, we don't know what X is. Now, the only reason that it turned, well, what color did they say? It turned, just a it's solution X and it turns what? A kind of brown color. What do we know has a brownish color? Iodine by itself. Iodine, when iodine is in water or in a solution, it has a brown color. Now, iodine, when it's joined to potassium, has no color. It's only when the iodine is by himself. So that means X kicked out iodine, right? I made a small mistake here. It's supposed to have small mistake here. Anybody see the mistake? Right? Oh Lord, that's why it wasn't making sense in my head just now. Right? That's not what. This is what happened. The X kicked out iodine, and now iodine is by himself. So we're trying to figure out what is happening in this question. Is it an this is an oxidation reduction reaction, right? Better known as a redox reaction. So let's work out the charges here. You all remember oil rig? Oxidation is the loss of electrons, and reduction is what? The gain of electrons. When X is by himself, what is the charge on X? Who can tell me, when you have something by himself, what is the charge on it? Correct. The charge on it is supposed to be what? 0. We should all know that by now. Potassium has a charge of +1 when it's bonded to something, and iodine is what? A halogen. He's in group 7. So he will have a charge of -1 when it's bonded to something. This is before the reaction. After the reaction, the iodine gets kicked out, and now the iodine is by himself. So the iodine gets a charge of what? 0. Potassium is still +1 because it's now bonded to X. Obviously, X must have a charge of -1 to stay bonded with the potassium. Right. So let's see what's happening here. X. We got a different color. That's a horrible color there. X. X went from 0 to -1. What happened to X? Was X oxidized or was X reduced? Remember, when a charge gets smaller, that's reduction, hence the name reduction, when the value of the charge gets smaller. If the charge gets larger by value, it's oxidation. So 0 went to -1. We all know -1 is what? Less than 0. So it was reduced. Right? What happened to the iodine? The iodine went from -1 to 0. He was -1 and then he increased to 0. That's right. 0 is larger than -1. So oxidation occurred here. Well, instead of saying reduce, I'm going to put reduction, right? So who is the reducing agent? Hear the word, eh? X was reduced. He experienced reduction. So who is the reducing agent? Right. The reducing agent is the other one. Now, you have to call the whole other one, right? Who is not X? Ki. So he is what? The reducing agent. Which makes who what now? The oxidizing agent. If oxidation happens here, then he is the oxidizing agent. The agent is always the other one, right? You can't be reduced and be the reducing agent at the same time. I think I had mentioned that, right? So what does X contain? Well, the only answer from the multiple choice you're going to have to choose. X is the oxidizing agent, right? So you can see this would be a very tough question for the student to resolve in what, a minute and a half, right? But the thing about it, this question not only comes in the multiple choice. I've seen the same question in the paper too, the structured part of the paper. All right, so this is all you all need to take down. What a circle in here. I want you to draw my diagram and everything, right? You obviously don't need to take down the wrong answers unless you really want to take down the wrong answers for fun, right? Right? You don't need to draw this or this because you already have those notes. All right, so I think this one is, well, it's a pretty easy one, considering we did acids and bases already. So which of the following is considered an amphoteric oxide? You all remember that amphoteric what? What's the acronym to remember the amphoteric what it's called, the amphoteric compounds? I even have not a purple, it's a pink zebra. A pink zebra. Right? So the A stands for what? Aluminum. Pink is lead, Pb, and zinc. So usually anything that is what? Has aluminum, lead, or zinc is called amphoteric. And remember, amphoteric can either react with what? An acid or a base. I just want to just quickly review, right? So if I have an acid plus an acid, if you mix two acids together, you normally get no reaction. If you mix a base and another base, you get what? No reaction. I put N, I mean NR. No reaction. But amphoteric, I'll put AMP. An amphoteric plus an acid will give you a reaction. R is for reaction. And even if you take an amphoteric and you add a base to it, you get a reaction. Amphoteric doesn't care. Give it a base, it will react. Give it an acid, it will still react. Okay? So, right? Right? So an amphoteric oxide is anything that contains what? Aluminum, lead, or zinc. So what do you all think the answer will obviously be? If they ask you for anything that's amphoteric, the key word here isn't oxide, you know. The key word is amphoteric. You're looking for one with either aluminum, lead, or zinc. So the only answer that could be correct is what? B. All right? Great. Right? So take down this, take down all four answers because I have no joke answers here. Circle the correct one. And what I know you all have this thing in orange, but take it down again. Take it down again, right? So nothing wrong with taking it down again. Oh, and well, if you want to take down back the acronym, anything with aluminum, lead, or zinc are considered ampho. I have the word in, I still can't spell it. Amphoteric. Right? So this was from last term. Right. So in this one here, what can be expected with the electrolysis of concentrated sodium chloride solution when using graphite electrodes? Now, I know you all, we did this in class sometime in September last year. But let's go through this one in detail. It's like an excuse to review it. So we're going to have concentrated sodium chloride. Now, when I say concentrated sodium chloride, that means there's going to be a lot of sodium chloride in comparison to what? Water, the H2O, because a lot of sodium is going to be dissolved in the water. So this means, well, the side that's connected to the positive side of the battery, as you all know, is called your anode, and that will develop a positive charge. And the negative side will, that you call that what? The cathode, and that will develop a negative charge. So that means since it's concentrated sodium chloride, you're going to get a lot of sodium. So I'm just going to put more sodium, right? And you're going to get what? A lot of chlorine in comparison to water. In water, you're going to get H and OH molecule ions. So we know the sodium is positive, hydrogen is positive, chlorine is negative, and OH is negative. So the sodium and the hydrogen is going to rush to the cathode side because positive is attracted to what? Negative. All the minus charges are going to be attracted to what? The anode. But when it reaches the anode, let's go to this table here. We're paying attention to the anions. Isn't OH easier to discharge than chlorine? Because as we go downwards, it's easier to discharge. So normally, I just say normally, if the anode had to pick between chlorine and OH to discharge, who under normal conditions would the anode choose? Let me know in the chat. Under normal conditions, it would correct. Normally, it would choose the OH. But here's the thing. We have a bit of a problem. It have more chlorines than OH. So it come like the chlorine said, OH, I know you are easier to discharge. but they gang up on OH and beat him up. And they become the preference now of the anode. So in a case like this, the chlorine kind of overpowers the OH. So the chlorine is going to get discharged. And of course, when the anode discharges chlorine, it's going to get chlorine neutral. And chlorine neutral doesn't exist, right? It exists at Cl2, which is why we get chlorine gas at the anode, right? Because it overpowers the OH. Now, I know the question I'm about to ask here isn't really, but you can turn back in your notes, right? Who gets discharged when they go to the cathode? Under normal conditions, who would get discharged? Who is lower, H or Na? Right. Normally, H would get discharged. But because it have more sodium, common sense would say, because of what we just discussed, sodium would get discharged. But does that actually happen at the cathode? Go back in your notes from last term. When it's concentrated sodium chloride, does the sodium actually get discharged? Or is it still the H? Turn back in your notes. Which one actually gets discharged? It's still the sodium. The sodium still no, not the sodium, sorry. The H still gets discharged. It's a kind of anomaly. So whatever logic we use for the anode does not apply to the cathode. You don't have to know why, right? The reason is sodium is so hard to discharge, even though if it have plenty of them, the cathode is like, sodium, you just too hard to discharge. I don't care if it have 1,000,000 of all you, and all you gang up on each. I'm still not discharging you all. That's just too much work for me. I'm still going to discharge each. All right? So I don't need you to draw anything. I just need you to take down this and the correct answer, right? And after this question, I'm going to show you all where to go on the website to download the slides for next week. I want you all to print it out because you're going to have to physically write on the slides, in the blank spaces on the slide. Oh, I don't need to